Okay. Hi guys. Okay, this video is for Algebra 2, Section 3.2, just the notes. I'm going to start off at the beginning. I know you're probably only missing the last few for most of you, but just in case anybody missed anything during class, I wanted to do the whole section. So this section covers solving systems of equations algebraically. So I'm going to go ahead and start off with the first slide. The first one we're doing is talking about solving by substitution. So when solving by substitution, you're going to reduce the system to a single equation by solving either equation for a convenient variable, and then you substitute that expression into the other equation. That way you're solving an equation that only has one variable. So let's look at an example. So in this case, I have a fairly easy one. The first equation, the 3x plus y equals negative 20. But the second one, we obviously can solve for y by plugging in x minus 8. And we would plug that into the other equation. So whichever one you simplify to solve for a variable, you want to make sure you plug that expression into the other equation so that you don't just end up getting a true statement. All right, so in this case, I'm going to take the 3x plus y, and instead of y, I'm going to place the x minus 8 equals negative 20, and this way I can solve for x. And then once I have that, I can go back and solve for my y. So in this case, I don't even need my parentheses because we're not having to distribute anything. That's a plus sign in front of it. So now I have 3x plus x, and you can plug a 1 in there if you need to. Remember, that's going to bring you to 4x minus 8 equals negative 20. And now I'm going to add the 8 to both sides. Internet's been a little funky from the storm that's coming through. Negative 20 plus 8 gives me negative 12. And I divide both sides by 4, and I get x equals, just make sure you keep it negative, x equals negative 3. All right, so now I can take that negative 3 for x. I can go back and use my y equals x minus 8. Y equals x minus 8, and I know that the x is negative 3. So y equals negative 3 minus 8, which means that y equals negative 11. So my solution for this system of equations, remember, it's always in the ordered pair x and y. And so my solution is negative 3, negative 11. There's my answer. So we have an independent, consistent system. We have one answer. All right, let's look at another example. This one, there's not quite such an obvious variable to solve for. We're going to have to simplify one. I am going to use this one to solve for y because the y doesn't have, it has a 1 as its coefficient, so that makes it really easy if I have to divide anything. So the first thing is I'm going to solve one of my equations, in this case the first one. I'm going to solve for y. You can solve for either variable. This one keeps us from having to have any sort of fractions, so we're going to go with y. So 2x minus y equals 8. We subtract the 2x from both sides. Now remember, the subtraction comes down with the y. That becomes a negative y. It doesn't just magically disappear, so keep it there. So negative y equals negative 2x plus 8. If we just change the sign of everything, that's the same as dividing everything by, or multiplying everything times negative 1. Get rid of that negative, becomes 2x minus 8. So now I can plug this 2x minus 8 into the second equation, have to use the second one, in order to solve for x. So second system, 12 x. I have 4 times x. Come on. There's 3. And now there's where I plug in my 2x minus 8. Y equals 2. So in this case, I do have to distribute. So that's why I kept my parentheses. 4x plus 3 times 2 is 6x. 3 times 8 is negative 24 equals 2. I'm going to do 2 steps at one time right here. I'm going to combine my like terms, but I'm also going to go ahead and add the 24 to both sides to move that constant over. And so I get 4 plus 6 gives me 10x equals 26. I divide by 10, and x equals 26 over 10. I'm going to go ahead and reduce that to 13 over 5, since both of these divide by 2. And so I get x equals 13 over 5. All right, so now I take that x equals 13 over 5. Excuse me. I'm going to plug that back into one of my equations. I'm actually going to use this one here since I'm solving for y anyway. So y equals 2. I could go and write that as a fraction since I'm multiplying it times a fraction. Minus 8. 26 over 5. I'm going to convert my 8 to 40 over 5. Since I can add fractions, I need a common denominator. 26 minus 40, 14. So that gives me a negative 14 over 5. And then I have my solution. I think I actually, yep, I gave y'all 2 slides to do this on. I keep forgetting I did that. So you're welcome to do that on the second slide if you need to. But that gives me my y equals negative 14 over 5. So my solution, which isn't pretty because it's a bunch of fractions, but it's still a solution. This is where you see a really great example of why solving algebraically, helps you get a more accurate solution, because solving graphically, you would never find these numbers. It would be really, and it would certainly be hard to graph them accurately because they're not like an easy 0.5, 0.25, 0.3 that you're going to find between two numbers. So there's our answer, and we could just leave it at that. All right, there's the slide that I gave you to do that work on if you needed the room. Let's go ahead and move to the next concept, though. The second way that you can solve algebraically is to solve by elimination. Excuse me. And so when we solve elimination, you add or subtract one equation from the other to eliminate one of the variables. Now, when solving by elimination, it is sometimes helpful to multiply one or both of the equations by a constant. That's actually what you're going to do the majority of the time in order to turn one of the variables' coefficients into the opposite of the others. So let's look again as a nice, fairly easy example here. So for my first one, I have x plus y equals negative 1, and I have 2x plus y equals 2. Now, in this case, we can see that our y variables have a coefficient of 1. So we can very easily, I'm going to take this first equation and I'm going to multiply it by negative 1. Because remember, I'm going to try to make my y variable completely go away. So I have to turn its coefficient into 0. So when I do that, my first equation becomes negative x minus y equals 1. My second equation, I'm not changing anything. It's 2x plus y equals 2. And now you can see that these two are going to cancel out. They're going to end up with 0. I'll plug that in there just so you can see it. But now you can add the other two, and we get negative x plus 2x gives us just x. It's like a negative 1. So 2 minus 1 is 1. And then this one is a 3. So x plus 0 equals 3. So that means that x equals 3. And so now we've already solved it. Once we do that, you can plug in that x value into any equation that we've got and solve for your y. So for the second step, I'll use the easy one, the x plus y equals negative 1. My x is 3, so 3 plus y equals negative 1. And I subtract 3 from both sides. I get y equals negative 4. And now I have my solution. All right. This next one is an example. I'm going to go back to my notes here. Right here. So when solving by elimination, it sometimes helps to multiply one or both of the equations by a constant. They don't have to be the exact same constant. And let me hold on. Give you an example of that. Okay. So in our example, note 4, you need to look at the two equations and figure out which one, which variable might be the easiest to eliminate one of your variables. In this case, I know that 2 is a factor of 6. So, and they're both positive. So what that means is I could multiply this entire second equation by -3 because I know -3 times +2 gives me -6. That would cancel out my y variable. So I'm going to do that first and then solve for x. So my first one doesn't change. I have 7x plus 6y equals -4. And then the 3, remember you distribute it to every single term inside the equation. So -3 times 5 gives me -15x, 6y, which is what I wanted, and -3 as my constant. So now my y variables are going to cancel. 7 minus 15 gives me -8x, and -4 plus -3 is -7. And I divide both sides by 8, -8, and I get 7/8. Okay. Nothing in here could ever cancel the 8 in the denominator. So to solve for my y, instead of plugging in that 7/8 x and having to work with all of these fractions, I'm going to use elimination again to cancel out my x terms. And this gives you a good example of when you have to use constants in multiply both equations by some constant in order to cancel out one of your variables. Did indeed give you 7x plus 6. I kept those in here, but I didn't. 5x plus 2. Okay, so in this case, because I'm going to have to solve for y, I have to get rid of my x's. Now 7 and 5, not multiples of each other, not factors of each other in any way, shape, or form. In fact, they're relatively prime. They don't even share a lower multiple, common multiple. So I'm going to have to multiply both equations by some number. I'm going to multiply the 7x times 5, and then I'm going to multiply it, because I have to make a negative now, I'm going to multiply it times -7. And remember, you're doing that to the entire, all the terms in the equation. Don't forget that. That's what allows this to work. So 5 times 7x gives me 35x, 5 times 6y, 30y, and then 5 times 7. -7 times 5 gives me negative 35x. That's going to cancel this out. -7 times 2, 15y, and -7 times 1, 7. So now my x terms will cancel out. 30 minus 14 is 16y, and -20 minus 7 is just -27. And this lovely fraction. But it's our answer. We have it. We're done. So our solution here. Go back to 7/8. Yeah. So x is 7/8. Y is -27 over 16. And we're done. All right. So that's solving the systems by elimination. The last part of this is all of the examples that we've had so far have been independent consistent. That means they're intersecting lines. They have one ordered pair that is their solution. So what do these algebraic solutions look like when you have an inconsistent system? So remember, when we have inconsistent systems, that means that they don't share any solution. They end up being parallel lines. And so they never intersect, they never overlap in any way. So they're not going to share a solution. What that means is when you solve it algebraically, you end up with a false statement. And that's going to indicate the graphs are parallel lines with different y-intercepts. It's an inconsistent system. So let me show you what that looks like algebraically. So in this case, with 8x minus 4y equals 1, 2x minus y equals -3. So in this case, because I have a y that has a coefficient of 1, yes, it's -1, but still, it's going to save me from any fractions. I'm going to solve this one by substitution. So solving by substitution, I'm going to solve 2x minus y equals -3 for y. So 2x minus y equals negative 3 minus 2x. Negative y equals negative 2x minus 3. And just come on, pen. All right, they're all negative, so I can change that to y equals 2x plus 3. And now I can plug this, I can substitute this expression into my first equation, the 8x minus 4y equals 1, and solve for x. So my second step is I substitute 8x. Just for this. Yep. 8x minus 4 times 2x. Don't forget to distribute, and don't forget that the subtraction distributes with the 4. So I get 8x minus 4 times 2x is 8x. Negative 4 times 3 is negative 12 equals 1. Okay, so here you see 8x minus x is 0. So I end up with negative 12 equals 1. Well, we know negative 12 does not equal 1. So you end up with no variable and you have a false statement. This means that you have an inconsistent system and your solution null or no solution. All right, that means it's an inconsistent system, parallel lines, there's no answer. Because get rid of a variable and you still have an incorrect or false statement. Negative 12 does not equal 1. All right, now when it's a dependent consistent system, it's solved algebraically, even with a true statement with no variables. Therefore, it means it's true for every ordered pair on one of the equations, or the line is also on the second line. The graphs are going to be coinciding lines with the same slopes and y-intercepts. So this is one of those things where you'll have a line and then the other line just exists right on top of it. They're identical. An example, to me, looks pretty easy. It looks pretty obvious it's going to be a dependent consistent. And they should, for the most part, unless you've got some really weird coefficients. But in this case, if you look at the second equation, 10x plus 15y equals 20, if you divided all of those by 5, you would end up with 2x plus 3y equals 4. So we know we're looking at the same line here, essentially. Both of these are going to be the exact same line. So, but I'm going to go through the algebra just to show you what it looks like. All right, so in this case, I am going to use elimination, because I know that if I multiply all, like the one who gives the x, if I multiply that 2 times negative 5, it's going to give me negative 10. It's going to get rid of the x. So let's go ahead and distribute that so that we can get our two equations. So negative 10x minus negative 20, and then I just rewrite the one underneath it. And you can see now that negative 2x, negative 15 y plus 15 is 0, and negative 20 plus 20 is 0. So we end up with a solution 0 equals 0, which is a true statement. Therefore, we have a dependent consistent system. And our solution, this means that every ordered pair exists in both. Just means they have all the same ordered pairs. All right, and that's when we have a dependent consistent system. And that actually is it. So that's it for our notes. I'm going to make a second video that covers the homework, the practice that we do for this section. And so I'll send that to you as soon as it's done as well. All right, thanks so much, guys. Talk to you later.